anyone who came in late, you're supposed to pay for your sweatshirt, t-shirt, crew, hooded, whatever this morning. And if you didn't have it, if you don't have it, you need to put a reminder in your phone to have it for tomorrow. Tomorrow is our last day of grace and begging to keep the cash box one more day. Okay, calendar. We are right here. We were supposed to have a test tomorrow, and a few days ago we were like, yeah, no, that's not happening. At least I was like that. You guys are probably like that for every test. But anyway, so I changed the calendar up, and it's new, and it's improved, and it's, well, I didn't put anything for yesterday. Seniors that were gone, hopefully check out the video. I will at least show you what we did. I'm not going to go over what we did. Watch the video yesterday. We did a great introduction, I think. We did a pretty good job, juniors and I. Oh, Haley came in. And Haley. In preparing to work on section 6.2b today. So our goal is to finish 6.2b. We've been working on 6.2a. I don't have the homework sheet up, but if you guys look at the homework sheet, it does start with 70 and 71. A junior, can you tell me why? Or a senior that watched the video?
Oh, because you have to work backwards.
You kind of have to work backwards since our section 6.2a, which I think is a great introduction to distant washers because it says the volume of a three-dimensional solid can be found using the integral from either x bounds or y bounds, in between I should say, x bounds or y bounds, of the area formula of the cross-sectional slices times the differential, which gives us our different three-dimensional slices or cross-sectionals that are accumulated with our integral. Anyway, volume equals integral of area, dx or dy. And that leads us into what we're doing in section 6.2b and why there is a pi r squared. Anyway, so I put 70 and 71 at the beginning because that's where we started, and then the rest of homework is distant washers. Tomorrow my goal is to go ahead and do AP practice. I have a worksheet hopefully being copied off in the office today, some multiple choice, some long answer. The rest of it will be probably due Monday/Tuesday. And I might give you guys some stuff in the book, or I might just stick with the AP practice and help us focus in on that. So I'll let you know tomorrow for sure. It kind of depends on how much work we get done on that AP worksheet as well, because it's really helpful, but it also kind of goes in depth, which can be a good thing, but can be a little overwhelming. For some of you guys, long story short, our test is on Tuesday. Okay? Not Friday, that's good. Right? Tuesday. Real quick, guys, just go ahead and give some sort of encouraging word to the people in your group, because some of you guys just are not looking good today. So turn around, give a high five, give a pat in the back, just be like, hey, you got this, or just like, hey, I'm thinking of you, cheering you on today, whatever you can do.
It was James' mom.
And here we go. All right, at least I have some half smiles. Here we go. Seniors, real quick, what you should have, and juniors, obviously, we talked about yesterday, you should have this page in your notes, right? You should have this page in your notes. And you should also have this page in your notes, and we're going to do some examples from both of those pages. To that end, actually, I forgot one quick thing that I wanted you guys to have. Some of our links went missing, sadly. Let me just go to last year real fast. I copied some stuff in the new folder, but not all of it. This was chapter 7 last year. It's our chapter 6 this year. And yes, let me go ahead and also open up your notes because hopefully the links work and I won't have to worry about all that jazz. Okay, we talked about yesterday. Let's do solid revolution. Let's not do that one. Let's not do that one. Let's do solid revolution. Let's not do that one. Let's not do that one. Let's do this method. And let's see if these actually open, but they look weird. All right. All that's opening in the background. Let's go back to our notes. Forever card number 48. Ooh, I don't know what that is. Let's just say run and hope that my computer doesn't explode. Go team. You probably shouldn't do that with your personal computer at home. Okay, so coming back. This is the forever card that we're going to be using for the following. I'm going to talk through some different things as to why, but once again, there was a great introduction given yesterday. I think we did a great job in getting ready for today. Long story short, when you revolve, when you rotate in order to get a figure, the awkward smart notebook thing is going to be there for a while. Does it actually let me? Oh, it does. Okay, back. Whenever we revolve, whenever we rotate. Last year, what did we rotate? Juniors, you already know this. Seniors, hopefully you listened. What did we rotate last year? What did we make? Parabola is to make paraboloids. Hyperbola is to make
Hyperbola.
exactly. And did you do anything else? Oh, yeah, ellipse is to make ellipsoid, ellipses, whatever. We rotated stuff, and when we rotated, we spun it. And when you spin it, look at the shape at the top. When you spin it, if you slice something that has been spun, what shape should it have as a cross-sectional area? Circular, right? Disk is if that circular region is going to be a solid throughout. What I was using yesterday was, hey, can you stick your finger in this thing being spun, or are you in trouble if you do that? Can you stick your finger in it, it's okay? No, you're in big trouble, right? If you stick your finger in the middle of that thing that's being spun, something's not going to survive. Something to do with your finger, okay? So a disk is completely solid. It's solid all the way throughout, okay? So we use pi r squared because of our formula from volume equals integral of area. So in this first example, I said disk, but did you guys see why it is a disk? Juniors, what was that word I used yesterday? Seniors, listen to the video. To describe when we have a disk for our volume. Flush. Flush against. The area between the curves is flush against who or what though? What does it need to be flush against in order to be able to be rotated and be a disk? Good. The axis of rotation, which in this problem, what is the axis of rotation?
Yes.
Careful. The x-axis, which is y equals 0, right?
Yes. Two.
Careful. Careful. What? Just because of that. No. Y equals 0, although easy mistake. Okay, so y equals 0, being spun. Now, we don't even really have to spin this shape, kiddos. We could, but we don't have to. As soon as we see the area is flush against the axis and it's being spun, we can say, sweet, v is equal to the integral of, I need pi, and I need r, and I need a squared. Now hold on, wait a minute. In your forever card, was the pi inside the integral or outside the integral? Inside. But does it have to stay inside the integral? No, because it's a constant. And constants can be brought, oh sorry, I went too far. Constants can be brought out. Now what's the dilemma with bringing the pi out? Some of you forget about it. Will forget about it, have forgotten about it, something to that effect. Now question. Help me out real fast. Why did you choose whether to do dx or dy? How did you guys choose, those of you that were thinking through this?
Because you see that there's
That's one way, Alan. Alan's saying there's a horizontal axis of rotation. That's one way, is just to memorize. Every time you go around a horizontal line, it'll be dx for discs or washers. However, there's another way.
if you draw like the little box, you see.
Yeah, if you actually slice it top bottom to spin it, what thickness would that have? Dx or dy? And the answer would be
Or you can do the little
dx.
circle.
And Katrina's also saying from yesterday, you could just look at the rotation arrow that you draw and say, hey, what thickness would this need to be a cylinder? And guys, am I going horizontally or vertically? My thickness, am I going horizontally or vertically? Horizontally, hence dx. Okay, all of those are ways to remember. You can actually draw the slice, but since you're already drawing the rotation arrow, you can just think about that third dimension, extending it to make the depth, that would be dx. So therefore, we do need to go ahead and have dx. Did you guys figure out your bounds then, if we need x bounds? Good, -1 and 3. So we're going to go from -1 to 3. We need a radius squared dx. The radius from yesterday, or from your forever card, is going to be the area of the region, because that is what gets spun. Does that make sense? And how do I do radius? Looking at the area between the region. Top minus bottom. And who's on top for this figure? Yeah, the y equals, which is the square root of 3 minus x. Remember, I need everything in terms of x. And what's the bottom in this figure? Yeah, y equals 0. Does that make sense? How many of you guys got there before me? Look to me and give me a thumbs up. Okay, a few. A few. I see some seniors that didn't quite get there. Maybe we weren't quite in that video yesterday yet. But You're getting some good examples down today. Maybe you need to go back to that video tonight. We end up with, remember I said to solve it by hand? Now we're going to do most of these not by hand or just leave them and say, hey, you figure out how to solve it. But in this one, if I have the square root of 3 minus x quantity squared, wait a minute, square root squared, what can I do, cool kids? Yeah. Can I just cancel them and then think about my calculator? Integrate, antiderive, what's the antiderivative of 3? Because that's who's left. 3x, right? What's the antiderivative of x? 1/2 x squared or x squared over 2. I am evaluating those from -1 to 3 because of fundamental theorem of calculus. Antiderive, plug in b, plug in a. So I'm going to go ahead and plug in 3. 3 times 3 is 9. 9 minus 3 squared is 9. 9 over 2 is 9/2. We'll just leave it at that. That's f of b minus plugging in -1. I get -3 minus 1/2. Long story short, put them all together. I'm going to distribute that little negative. 9 plus 3 ends up being 12. -9/2 plus 1/2 ends up being -8/2, which would be -4. So I have 12 minus 4. Anybody else get 8 pi? Double check my math though. 8 pi, 8 pi. 12 minus 4, 8 times pi. Would you be right if you wrote 8? No. But would you be right if you wrote 8 pi? Yes. Huh? This one? Yeah, if it was like a long answer, you could have left it here. I was just assuming this would be more of a multiple choice one. It just depends. Questions? Okay, then guess what? You guys should be able to. Woo-hoo-hoo! Go. Don't worry, we're skipping example number 2 on purpose. We're doing number 2 later because he's a washer. Which is the second page of notes. Ready, set, and go. I'm not going to give you tons of time, but I'm going to go over and make sure I have those illustrations ready to show you. As you guys work on the next disc example. Please feel free to reach out to your groups, okay? Please feel free to reach out to your groups. Alright, kiddos. So let's see how we did in the example. I'm going to start solving. Let me do it kind of quietly, that way you guys can quietly check. Now this is the setup for the answer, but I'm going to ask you some pointed questions. You ready? Why did I choose dy? It's around the y-axis, which means it's around a vertical axis of revolution. But why did I show this shading right here? If you were to add depth to this rotation arrow, is that a vertical depth or a horizontal depth? And y is that a way of remembering? Vertical goes with y, right? Okay. So without even drawing anything else, you can look at that rotation arrow and say, hey, at least I need a dy. Ah, see how my signs go up? Katrina's asking about this little negative over here. Question, why did I have to solve for x in the first place? because I need everything in terms of y. So I took my function, which is given over here. I had to solve him in terms of y, right? But I didn't like that little negative in the bottom. I'm like, ew, that's gross. Now I could have made it negative 1/2 times y minus 3. I could have just done that. I went ahead and set out like negative, so I actually kind of flipped that negative up. I divided each of the top terms by the -1, so hence the 3 became a positive, the y became a negative. That's just common kind of simplifying practice. We don't like negatives in the denominator. Then I said, wait, but if I have to integrate this thing by hand, ew, gross. I'd rather it be 1/2 times 3 minus y than 3 minus y over 2, which looks like a quotient. Now, which function was that, right or left? How do you know? When you come over here, you say, okay, from the axis, go out. Go to the right. From the axis, go to the right. Who's on the right? This guy. Who's on the left? Well, hold on. So if x equals 1/2, 3 minus y is on the right, who's on the left? X equals 0. Sometimes if the axes are my boundaries, it's a little bit hidden as to what's on the left. But we can say x equals 0 is on the left. So with that, I did too many strokes in that one. Bummer. There we go. We came down here and I plugged into my formula. And I said, sweet. Pi times the integral. Wait, why did I do 0 to 2? Y bounds, right? Y bounds. We go from y equals 0 down here at the bottom to y equals 2 up here at the top. From 0 to 2 of my right function, there he is, minus my left function, there he is, dy. Now, let me give you a few illustrations, more further illustrations of this, just real fast, okay? If I was to go, let's do this one first. What makes a disk? Oh, I didn't hit start? I thought I did. I apologize. There we go. There's a curve. Let's say we're looking at the area between the curves. Let's say that area is revolved around. If that area is flush with the axis, that figure is a solid. Now they're showing arc length right now. That's something that's a little bit more of a BC topic. We don't have to find the surface of the solid revolution. Now they're showing volume though. A slice would be circular, and we can't do that. What we can do is an actual cylinder, pi r squared times depth. And what happens, we say, hey, we can't do the nice little curvy thing. We have to find the cylinders with that straight across, which would be all segmented like those kids' projects. Let me show you another example of that. This is what we can do. We can do them segmented to where it's not smoothly across. But then we say, hey, if only we could fit more and 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 more infinitesimally, if we can make those infinitesimally thin, kiddos, what are we converging or approaching? The actual volume of the solid, which you can't really see because all of those thingies are around, but the actual volume of the solid. We're trying to approach the volume of, now do we have to do any of that by hand work of the limit as the number of these disks go to infinity? No, what does that for us? The integral. This little thickness, the integral with that d, that differential says, hey, let's make the thicknesses infinitesimally thin and let's accumulate from 0 to 2 all of that volume. And so in essence what you're doing is you're moving through, or the integral moves through, and in a way, is adding together two-dimensional objects, two-dimensional areas, in a way, is doing the impossible and accumulating two-dimensional areas to make a volume, which is technically impossible. So what it does is with this differential, they're actually three-dimensional, where it's having the thicknesses approach 0. Some of you are interested in that theory, some of you are not, but it's crazy that, in this sense, an integral takes an area and is able to accumulate two dimensions which actually have no depth to somehow make the depth of a three-dimensional figure. Kind of cool. Doing the impossible. But kiddos, what is different as soon as we get to
And you have to
really
do
quickly,
it twice.
can you guys tell? Where is this figure, this area between being revolved around?
The x-axis.
Ooh. And question, what happens when we revolve around an axis that the area is not flush against?
You have a washer.
There is some sort of hollow, there is, why aren't you moving? some sort of hollow region in between, right?
Donut.
That's a face.
Kind of a snazzy one though. There's some sort of hollow region in between, and when I say, can you stick your finger in it? Question: would your finger be okay in the middle of that thing? Yes, as long as you don't have a really fat finger. So anyway, come back. But long story short, when an area of a region is not flush against the axis it is rotating around, we're going to be in some trouble. So question: why am I showing you that before us looking quickly at? Oh hey, we'll get back to that in a second. Going to practice this idea. Once again, listen to the video yesterday. Seniors, please just hear me out. Listen to it. I go through these ideas in depth. Long story short, in order to find the volume of this weird thing, which is similar to what we just saw, we have to do, guys, remember from yesterday? The whole thing minus the hollow, right? The whole thing, why am I saying that? Because otherwise, if I say whole, you think I'm saying H-O-L-E, and we're just in trouble. So the whole thing minus the hollow. You got to punch out something to get that hollow in between. And if you guys look at the figure above, hopefully that helps. Once again, listen to the video yesterday for more depth. But we get to the formula for, formulas for, forever number 49. Big R is talking about, you guys just saw it. If it's coming first, what's it talking about, whole or hollow? The whole thing. Little r must be talking about then the hollow. The whole minus the hollow. Pi big R squared minus pi little r squared. Dx or dy? So, why am I showing you this right before we go to this example? Is it flush against? And the answer is no. Is it flush against? The answer is no. This is our next example. We're actually going to do it all together. This is our next example. We're actually going to do it all together. But once again, if you guys can't tell, the area between the curves, similar to the one that you just saw, is going around an axis, which it does touch at one point, and that's great and all. But does it follow the entire axis? Is it flush against? And the answer is no. So since it's not, when you spin it, there will be a hollow. So what we need to figure out is, well, a few things. But first of all, let me write the formula just since we're still getting used to it. V is going to be equal to the integral of pi big R squared minus pi little r squared. Two separate ones. The AP loves to trick you, and on a washer problem, when there is a hollow, they love to put in multiple choice answers just 1 pi r squared and make you think that's right, but you have to know that's wrong. Ooh, life lesson. We have to know the truth so that when error comes up against us, we recognize it, right?
Yeah.
Because doesn't error sometimes look an awful lot or sound an awful lot like truth?
Yeah.
That's why you have to figure out what is your truth to be founded upon. What would I say? I think the Bible is total truth. What would others say? Well, God takes science as total truth. Man's representation of God's creation. Okay, coming back. So, dx or dy?
Yeah.
Why?
It's spinning around the axis.
If you don't like drawing the figure, just say, hey, is it going to extend horizontally or vertically to make a cylinder? The answer is horizontally, hence it's going to be a dx. If you want to memorize a horizontal axis, does that work also? And the answer is yes. You can also memorize it's a horizontal axis of revolution. Big R. Here's the way you have to remember it. Please, please, please. Did I do any color coding yesterday? Oh, I did. Navy blue was big R and the fuchsia, whatever, was little r. Okay. Coming back. Okay, so navy blue. The way that I always think about it, I don't know, it just helps. Believe me, these problems are about to get harder. Think the center of your revolution. Think the center of your axis of revolution, and then extend upwards as much as you can. Or I should say, extend to the outermost of the curve. I shouldn't always say upwards. But since the area is above, I'm showing going from the axis up. Always start from the axis when you're doing your radii. Always start from the axis. Believe me, just trust me. Start from the axis because that is your center. Get centered. Ooh, we could do a life lesson on that. I know, I see that question. Hold on, give me a second. Start from the center. Extend to the outermost. Go find the area wherever he is, above or below, and extend to the outermost as far as you can along that vertical line. I'm just choosing one representative slice, guys. You could have drawn it here, it would have been similar. You could have drawn it here, it would have been similar. I just chose a spot. From the center, extending up to the outermost. That will be your capital R. What am I going to do for little r? Start at the center. Extend to the outermost of the hollow. The outermost of the entire thing will be for the whole thing, the outermost of the whole thing, and then the outermost or the edge or the boundary of the hollow. The reason I do them a little bit separated and not together is just to represent, because you guys are probably doing this with one color just for you to be able to clearly see the difference. Does that make sense? It'd probably be a little bit better if I were to do them in the exact same position. So if I were to actually move this guy like right on top of that guy, that'd probably make a little more sense, but since you guys only have one color, I kind of remove it. Now we're going to go ahead and apply that, but Ella, go ahead. Now's a good time. What's your question? Let me finish this example first. So then we have D, no, not dy. What did we say? Dx. Good. So I need some x bounds, right?
Yeah.
Can we tell the x bounds from the picture since it's given to us?
Yeah.
Okay, it starts at x equals 0 and it goes until x equals
1.
Do you see it? Because 1 would be the intersection point. We still use the idea of intersections if we have to find it ourselves, like section 6.1. So I can go ahead and plug in right now, 0 to 1, but we need to figure out who is the big R and who is the little r, right?
Yeah.
So here we go, to plug it in. B is equal to, yeah. I'm going to go ahead and leave the pi in for one more second. Katrina's saying, can you just pull out the pi since it's shared? And the truth is, yet again, yes. But I see, once again, one of the most common mistakes in these problems. If you understand how to do it, forgetting about poor little pi. Forget pi day, you can't forget about him. That's his party. Okay, coming back. I need pi times the big R squared minus pi times the little r squared. And all of that needs to be in my big old dx formula. Okay? Now, can we zoom in on big R for a second? Is that okay?
Yeah.
We know we're doing top minus bottoms. We know we're doing top minus bottoms. So we have to figure out which top, which bottom. For big R, question, what's on top?
Y equals 2 minus.
The parabola. And the parabola, they told us right over here is
2 minus.
good. 2 minus x squared. That's our function on top. Right? What's the bottom going to be?
X equals, y equals 0.
Which is the exact same thing as the
No.
axis of revolution. Okay, that's a hint. Which is the exact same thing as the axis of revolution. So when we go to plug it in, give me 1 second, Brandon. Since we're allowed to do everything in terms of x, we're just going to say, sweet. Let's take the top, which is 2 minus x squared, minus the bottom, which is 0. Now, some of you are starting to see, hey, can't we just shortcut and forget about the 0? And the
Yeah.
answer is yes, if the axis of revolution is a 0. But what about this example I'm about to show you where the axis of revolution, why is there a random line at y equals -1? What's going on at -1? Where are we revolving around? That's kind of hard to see. You're not revolving around the axis, you're revolving around a different horizontal line. So if some of you are like, can I just forget about the -0? No, you have to get in the habit of looking for a bottom, because what if you were subtracting y equals -1? That counts. Okay? Coming back. Little r. Yep. Little r's top, if we were to look at him. The top of the boundary is going to be y equals x. That's that line that's right on top, the green line. And what's going to be the bottom? The nice thing is, isn't it the exact same? Isn't it the axis yet again? So we're going to go ahead and plug in and say, okay, we have top, which is x, minus bottom, which is 0. Now, can we make this look prettier? Yes, but only once we have it all set up. Some of you are like, can we now pull out the pi? Fine. I'm just going to say, don't you dare forget about poor little pi. Okay? Well,
Go ahead.
here's the problem. It could be a calculated question. It could be a express but do not solve question, and this is the multiple choice answer. Ooh, that'd be nice. It could be a calculated question, plug and chug it, don't forget your pi. Most common mistake if you understand what you're doing. It could just be state the expression, that would work. But could you do this by hand? And the answer is most definitely, assuredly, yes. But would you want to use U sub? And hopefully all of us say no. What am I going to do since it's simple? I'm going to FOIL it. And I'm going to get 4 minus 4x squared plus x to the 4th minus x squared. And I'm going to say, hey, this is a power rule waiting to happen. I'm just going to go one more step before doing it because I see some like terms in here. 4 minus 5x squared plus x to the 4th. Once again, on the AP, who knows? Could be a plug and chug to a calculator problem. It's a decimal. It could be plug and chug this part and it's a decimal with a pi next to it. It could be a state the formula. It could be a solve by hand. It's all dependent on what the multiple choice answers show. And it's dependent on, sadly, whether it's in the calculator or non-calculator section of the AP. 4 times x minus 5 thirds x cubed plus 1/5 x to the 5th. I'm solving one by hand just for illustration that you might have to solve it by hand. We end up with, hey sweet, if we plug in 0 to this guy, what's going to happen to everybody? 0, 0, 0. So all we have to plug in is really just the 1. So we're going to have pi times 4 times 1 is 4 minus 5 thirds plus 1/5. Technically it would be minus 0. At the end of the day, I would just say common denominators, which kind of stinks, but it's possible. I see 15ths, right?
Yeah.
So I could say 3/15. I could say times 5 minus 25/15. And I could say 4 times 15 is 60/15. Double check my math real quick. We end up with negative 22, and then 60 would be negative 38/15. Positive, sorry, yeah. Whoa. I was like, wait a minute, volume can't be a negative. That's a bad sign if you get a negative. Actually, that was pretty good. You guys double check, is it 38/15? Okay. Done, till I'm done. Ella, you can go ahead and go, now's a good time. Okay. Oh my goodness, wait a minute. Whoa, what do I have on the last page of your notes? More illustrations and examples. Wait, pause. You start packing up and you start checking out. Why have I told you, go check out CalcAB, which, pause, just a quick heads up. You guys, you've seen the link, you've already written down the link, don't go to that one, he probably has changed it by now. But this is, he does have specifically on solids of revolution, so does Patrick JMT, and I actually like his explanation. Kiddos, if you go to Con or if you go to Patrick, why are we talking Charlie Shush? Thank you. If you look at any of those, they're going to talk about, or they're going to have some sort of volumey things where they talk about cylindrical shells. This is not, pause, this is not an AB topic. This is a BC topic. Okay? Kiddos, what's your job tonight? Work on 6-2. Homework 6-2 tomorrow. If you have your Pi Day extra credit, throw it in the back tray by the end of the day. Technically, sorry, end of the day.
Look at my fan.
We got so distracted with other good things today. You guys did great.